Hello everyone. So I did some topology last time. I defined topological spaces from first principles. I've had a really busy week. There's a Lean conference going on this week in Germany. And oh, thanks for the link, James. And so I've been very much distracted by that. And so let me revise what we did on Tuesday. On Tuesday we defined a topological space, and it's a collection of it's a predicate on open sets of X. It's a predicate on sets of X, on subsets of X, called is open. So some subsets of X are open. Remember, a term of type set X is a subset of X. So it's a predicate on subsets of X, i.e., a way of saying whether some set, it's a way of saying some sets are open. And then what axioms does this open thing have? The whole space is open. The intersection of two open sets is open, and a union of a set of open sets is open. And then we did this kind of parameterized version as well, the Bourbaki version. We've got a random type and then a function. We've got a collection of open sets parameterized by that type, and we proved those were open as well. We proved the empty set was open. We proved that a finite intersection of open sets was open. We defined what it meant for a set to be closed. And we didn't prove much about closed sets at all. And we defined a continuous function. A function was continuous if the preimage of every open set was open. We proved that the identity was continuous. We proved that the composition of two continuous functions was continuous. And then we defined compact. And when I wrote the definition of compact on Tuesday, I hadn't actually finished the proof that a continuous image of a compact space is compact. And now I've finished it, and I think that it's neater if we redefine compact, right? So this is still the definition. Our specification is still the same. As mathematicians, we want to say a subset of a topological space is compact if every open cover has a finite subcover. So that definition is fine, but we can still modify this and come up with different equivalent definitions. So, maybe while I'm here, I should tell you, interestingly enough, I'll just cut and paste. This is direct from MathLib. MathLib's definition of a compact set is a set's compact if for every filter that contains S, every set of F also meets some. I mean, there's just some crazy definition involving filters. So I don't want to go down that path. In some sense, this is an experiment to see why setting things up normally. By normally, I mean with open sets and open covers and things like that, the way we normally learn it, why filters are preferred to that. So we're not going to do filters at all. We're going to do it the way I was taught it by Ray Licorice. But Lean has several ways of explaining that things are finite. So I want to modify this. I want to do this the Bourbaki way. So I'm going to change my definition of finite. So finite means for all, I'm going to have an indexing set. So if I've got an indexing set iota, and if I've got U, which is U is not going to be a set, U is going to be a map iota to set X. So this can go. This isn't what it's going to say anymore. So I've got a random set iota, and then I've got a function that takes an element of iota and spits out a subset of X. And if these things are all open, basically I'm saying I've got a parameterized family of open sets. So let's say also we have HU that says for all I of type iota is open U of I. There. So far I've managed to say I've got a random collection of open sets, and this collection of open sets is indexed by a type iota. And now let's say this collection of open sets covers C. So HC, let's say that says C is a subset of the big union of over I of UI, right there. So that says I have a cover of my compact set by a random collection of open sets, and then the claim is that there exists, these should be like this really, there exists some subset of iota which is finite, finite F, and C is a subset of, and again it's a big union big cup, and now this would be the union for I in F of U of I. There. So that's my definition of compact. I've changed the definition, but fortunately we didn't prove any theorems about compact sets last time. And so, you know, as an exercise, one could prove that this definition is equivalent to our old definition. But I'm not going to do that because my definition, I think this definition is more, so maybe I should say, you know, I think this definition seems to me to be easy to work with. There. So I'm going to go with that for my definition of compact. These are, you know, it's still the mathematical. I haven't changed the definition. I mean, I have changed the definition, but I haven't changed the specification. I've only changed the implementation. And my definition of Hausdorff, I think, is fine. And then let's start by proving this theorem. You know, first theorem today: the continuous image of a compact set is compact. So here's the big theorem, and let's see if we can do it. So, and let's also move things around a bit so I can see the chat. Although I've noticed that other chatters are very good at dealing with chat questions. Right, so we're all ready. Let's prove that continuous image of a compact set is compact. So what does the definition of compact mean? We can see what it means, right? You know, the goal says, I mean, I'll unfold it if you like. Unfold compact. This is what we've got to prove. By definition of compact, we have to prove some random thing, but we don't even need to do it really. So we can go intros iota. So let's assume we have a type, and then let's assume we have a function. There, we've got iota is a random indexing set, and we've got a function for our indexing set to the subsets of y. And let's also assume that that whenever we evaluate that function, we get an open set. So U is really a function from some random set to the set of open subsets of Y, because Y is a topological space. Y is our target topological space. And let's also assume that that C is covered by this union, right? So let's do HUC. So HUC is the assertion. Sorry, that's not C. C is a subset of X. Let's assume that we're trying to prove that the image of C is compact. So let's assume that the image of C is covered by all of these open sets U of I. You see, you know, this says in maths language, this just says f of C is a subset of the union over for I in I. There, I of we would write UI normally, right? That's how I'd write it on the board, probably, if I was lecturing it to undergraduates. I've got some random indexing set. Do you know what I'm going to call it? I want to call it capital I. Let's call it capital I. Do we use capital I for anything else? I don't think we do. There we go. We don't have the open interval. So this is what. So HUC says that, right? There. So the image of C is covered by all my open sets UI. And now the question is, and what we want, you can see the goal now. There is just a finite subset. There is just a finite subset of I, such that the image of C is covered by this finite subset. And now, of course, we're stuck, right? The next, you know, if we wanted to work on the goal more, our next line would have to be use something, right? There, that's somehow the only thing we can do. And we haven't got anything to use yet. All we've got is this random set I, and we don't have any finite subsets of that set lying around. So where are we going to get a finite subset of that set? Well, obviously we're going to have to use the fact that C is compact, right? So let me tell you the math. Maybe go through the maths proof, right? What's the maths proof? So maths proof, it suffices to prove that if f of C is covered by open sets, it has a finite subcover. There. So now here's the trick. So say we've covered f of C by open sets. Then we've covered C by open sets, right? C has a cover by open sets, namely F inverse of the UI, right? So there's a finite subcover, say whatever U1, U2, well, let's say F inverse of whatever, F inverse, oops, F inverse of U1, F inverse of U2, etc. F inverse dot 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 F inverse of UN there, and now we check that C is covered by C is contained in the U1 union cup U2. I could do this, right? Cup dot 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 cup UN. There we go. So that's the maths proof. That's what we're going for. Right. So we've got that far already. So now what do we need to do? We need to make this then. So let's define. Okay, let's define V. Let's define V from I to set X. There, and it's going to be the function that takes I to kind of F inverse of U of I, right? There. And so now the claim is, you see, this is a sketch proof, really. So the claim is, well, I guess the first claim is that all these sets are open. And see as I go, right. So let's check that this covers C and that all the F inverse. Yeah. So let's define VI to be this, right? Oops. VI to be F inverse of UI. There. So now let's check. So now let's check this covers C and that all the VI are open. So the fact that the VI are open is easy, right? Because the UI are open and the preimage of an open set is open if our map is continuous. So let's prove that first. So have HV that says for all I and I is open V of I. So why is that true? Let's put it in a little. Let's do that. Why is this true? This should just be easy. So let's let little I be in big I. And now how are we going to prove this? Let's just apply F. No, let's apply the fact that F is continuous. We need to use the fact that F is continuous. So let's try this. Apply HF. Let that's worked beautifully. And so now we've got to prove that UI is open. And so now let's apply HU. And that's done it. Goal's accomplished. Wonderful. So now we know that all the VI are open. So that's done. So let's check that all the VI are open. Great. And now let's check. Let's check that the VI covers C. Right? And why do they cover C? Because we know that F of C is covered by the UI, right? Oops. So let's check that the VI covers C. So what are we going to do? Well, I guess this is the only cover of C we're going to use, right? So we could specialize. Oh no, let's not do that. I don't know. Okay, let's do it. Okay, let's have HVC. Yeah, let's do this. That C is contained in the union over I of V of I. There. And that's not, oh, that has worked. So why is C contained in the union of the VI? Well, let's just prove it. Let's just run at it. So I don't know, intro, have we got an X? Let's intro X. Let's let X be an element of C. And so let's intro HX. HX is the hypothesis that X is in C. So now we have an X and the X is in C. And I've got to prove that X is in the union of the VI. So which VI are we going to use? Well, I guess we're going to use this fact now, right? We know that F of C is a subset of the union of the UI. So we need to check that X is in the union of the UI, right? So we've got, so let's have hx2. We need to check that f of x is in the union over I of the UI, right? And why is that true? That just must be obvious because, so we just apply HUC there. And so now we've got to prove that f of x is in the image of f, and that's going to be true because of hx, right? So use x or something. Use x. Oh, I see. So we can use. We have to prove that x is in C now, and that's hx, and then the last thing is refl. So that's done that. So now we know that f of x is in the union of the UI, and so now we have to prove that x is in the union of the VI. How are we going to prove that x is in the union of the VI? I see. F of x is in the union of the UI, which means that f of x is in one of the UI, right? So we can rewrite. We need to get the I, right? Yes. So what are we doing here? So we know that f of x is in the union of the UI. Over I of UI. So there exists an I such that f of x is in UI. There. Maybe I haven't said what I was. Yeah, here we go. Let's check the VI. So say x is in C. Say x is in C. Then x is in the big union over I of UI. There. Oops. Of UI. No. Then f of x, sorry, is in the union of the UI. So that means that it must exist an I. So how are we going to get that I? You see, we've got f of x is in this union. So this somehow must be equivalent to the fact that there exists an I such that f of x is in UI, and that's going to be called something. I don't know if that's true by definition. Let's see if there's something called rewrite mem union, mem capital union probably. Yeah, look, mem union. That's what we want to do. And while we're here, we may as well rewrite it to the hx2 and at the goal. Yeah, wonderful. So now hx2 says that there exists an I such that f of x is in UI, and let's get it, right? Case is hx2 with I in hi there. And now we've got to prove an existence statement. There exists an I such that x is in V of I, so obviously we're going to use the same I. We're going to use the same I, and now x is in V of I. Well, what's the definition of V of I? V of I is the pre-image of U of I. And so what does it mean to be x in V of I? I think that by definition means that f of x is in U of I. So I'm going to be a little bit cheeky here. I think that this goal here is definitionally equal to this goal here. So I'm going to put exact hi and see if it works. And it does. There. So there we've got no errors down here. So we've checked that the VI covers C now. Yeah, so C is contained in the union of the VI, and all the VI are open, and so we're in a perfect position to apply the fact that C is compact, right? So let's specialize that C is compact. So let's specialize HC. So now what does we want? We have a cover by I, and then the sets of V. Does that work so far? And now we have to, you see, I'm changing the type of HC. HC is a function, right? HC now wants an input of this, and we have that already. That's HV. So let's feed in HV. And now what? C is still a function. You see this arrow thing here. So now C wants a proof that C is in the union of the VI. And we've got that. We've got a proof of that. It's HVC. So it's HVC. There we go. Wonderful. So now the fact that C is compact, so there exists a finite subcover of the V's there, and we can get that with the HC is a hypothesis and it's an exists, so we can cases it, right? We can do R cases HC with F and HF. But HF will be lots of things. Yeah, you see HF is an AND. So this is HF, comma, HFC. How about that? Right, wonderful. So now we have F, which is a subset of I, a set of elements of I, if you like. It's a subset of I, and F is finite, and C is contained in the union of the VI for I in F, which is wonderful. And of course, I see, so great, there exists a finite subequivalent of the VI. Now, I claim that the corresponding finite, the corresponding UI will work. So, where's my goal? I've got to now prove that there exists a finite set F, and you see we have a finite set F here, so we can use F HF. Now let's use that. Great. And so now we've got to prove that the image of C is in the union of these things here, and we know now. I suspect I won't be so lucky here. I suspect that HFC implies, oh, but it's not equivalent. Yeah, we can't. Exact HFC won't work, right? Exact HFC, not a chance. No, it doesn't like it. These HFC is not definitionally equal to the goal. In fact, I think that's right. I think the goal can be true and HFC can be false somehow, like if H is a constant map. So how are we going to prove the goal? We're going to need, I mean, HFC is the key thing. So let's check they cover F of C. So let's take an element of F of C. So intro Y, intros Y and HY there. And HY is a slightly kind of a rubbish thing, right? HY is a proof that Y is in F of C, but we can, what's the definition of Y is in the image of F? The definition of this is that there exists an X such that Y equals F of X. So we can use rintros here. We can break this up, right? We can do pointy brackets X comma HX, I would imagine. Have we got any X's? No, we don't have any X's. And you see HX is two things. HX is firstly a proof that X is in C, and secondly a proof that F of X is Y. So we can do HX1, HX2. There, and now HX1 is a proof that X is in C, and HX2 is a proof that F of X is Y. But Y is just an atom, right? We've only just made Y here, right? So we could define Y to be F of X. That would be a good idea. So let's remove that Y there, and let's change this to be refl. There, so it's true by definition. There we go. And now Y is equal to F of X by definition. You see our goal has changed. Our goal has now got an F of X in, right? Before that, when I had HX2, when I had a Y and an HX2, the goal will have had a Y in. There, you see the goal is now Y is in something. But if I define Y to be F of X, it's just a convenient thing to do by putting refl here. Then immediately our goal, you see H has only just been born, but now F of X has only just been born, sorry, but now F of X is in the goal. So how am I going to prove that F of X is in this union? Well, X is in C, and C is a subset of that. So maybe we can specialize HFC, can we? Specialize. You see, this is a slightly subtle use of specialize. Specialize is when you have a function, right? HFC does not look like a function, right? HFC looks like the claim that something is a subset of something else. But this what does it mean for A to be a subset of B? What does that actually mean? For A to be a subset of B means that it means every element of A is an element of B, and so it's a function that takes an element of, you know, it takes an element of whatever it is X, and then a proof that it's in C, and it spits out a proof that it's in here. So HFC is a function. I suspect I can specialize it. Specialize HFC. Why don't we give it X? No, it hasn't worked. I mean, it hasn't worked. That's a shame. I see. HFC is a function. It wants a proof. I see. It wants HX1. And that has worked. Great. So HFC is now a statement that X is in some union of the VI, and we want that f of X is in the union. Right, I think we need to take these, I suspect we need to take these unions apart. Let's see if I can use mem union. This is not the same kind of union as this. This is a union over all terms in the type, and this is only a union over the terms in the type that satisfy some property. And so this is a bounded union. So maybe I can rewrite mem B union. No, B union is not an implication. B union if is an implication. Let's try this. Can I do that? Yeah, at HFC and the goal. There. How's that gone? So that's great. That's the same trick again. And so now HFC claims that there exists some element of I with some property, and we need some element of I with some other property. I bet we still can't do it, can we? This is really kind of annoying. Exact HFC. They won't be... Yeah, they're not equal... Oh, no, they are equal by definition now. Oh, I've finished. There you go. I finished slightly earlier than planned. So there's... In fact, could I have done that there? Exact HFC. No, it doesn't work. I don't know why it doesn't work there. Hard luck. You had to rewrite mem union if. So let's check they cover H. Yeah, let's check they cover HFC. I just did. They do. They do. So the cover of f of c had a finite subcover, and we're done. So that's the end of that proof. So now let's move on to this. Compact subspace of a Hausdorff space is closed. And unfortunately, to do this, so to prove that a compact subspace of a Hausdorff space is closed, we need the fact that a locally open set is open. So this is a lemma we need along the way. So I want to prove. I'm going to prove. So let's prove a lemma first. So let's prove that. Let's prove that first. So lemma open if and only if locally open. So what does this say? This says if V is a subset of X, then V is open V if and only if for every element of X. If X is in V, then that there exists a U such that X is in U and is open. What I'm saying is a set is open if and only if every element has an open neighborhood. That's what I'm trying to say here. Having an open neighborhood is like being, if every element of V has an open neighborhood contained in V, is open U, and U is a subset of V, right? There. And this is quite interesting because this is slightly delicate. So we've got to prove that V is open if and only if every element of V has a little open neighborhood that's contained purely within V. And the reason this is delicate is, so one way is easy. Let's do the easy way. And I was slightly surprised that the other way was harder. So what's going on here? What's the goal? So intro HV. So what's going on here is we've got V, which is a subset of X, and we've got a proof that V is open. And so now we're trying to prove. So this way is easy. This way is easy. Say V is open. There. And let's say X is in V. So intros X and HX. Now we've got to prove that there exists some open set such that X is in that open set, and that open set is a subset of V. But V is open, so we can just use V, right? Use V. We want an open set. We want an open neighborhood. We want an open neighborhood of X contained in V. Let's just use V. There. So use V. And And so now we've got to prove lots of things, and they should all be easy. So this is, I guess x is in V, that's hx, so we can use hx. Is open V, that's hv, use hv. And the next goal was refl, which the system did automatically. Had to prove that V was a subset of V. But last goal, V is a subset of V, closed automatically by refl. Because whenever lean does a, so this use is, yeah, I don't know. It was closed, for some reason lean ran refl. Maybe after use, lean always runs refl. And being a subset is a reflexive relation. So that way is easy. And now this way, I'll show you why it's a challenge. So now let's go this way. Let's intro H. And now what have we got? Let's have a look here. So we now have this hypothesis that for every element of V, there exists some U such that X is an element of U and U is open and U is a subset of V. And now we have to prove that V is open. And so, of course, what we want to do is we want to run this function, right? We want to go through all the elements of V, feed them all into H, and then for each one of those elements, we're going to get some set which is open and contains X, right? But the thing is, there might be more than one set, right? Obviously, you know, if V is a big ball, and X is in V somewhere near the middle, then you could be a small ball or you could be a slightly larger ball, right? You could be a ball of radius r for any sufficiently small r. And so for every element of V, we're going to be able to choose an open set, but that means we have to make infinitely many choices all at once, so we kind of have to use the axiom of choice. See? This is kind of annoying because we don't really want to use the axiom of choice. But the natural way of doing it, and indeed there's a Zulip thread. Maybe I should post some spoilers. Where's the Zulip thread? If you want to see, where's this thing? From exist to sets. Here, I'll just post this link in the chat. If you're on the Zulip, then you can see. So I did this using the axiom of choice. That's the proof. Using the axiom of choice, and it wasn't much fun. But then Reed Barton, thank you. I kind of have this belief that Reed Barton is some kind of cult figure on the internet. Where's Reed Barton? Well, Reed Barton was on Zulip earlier today, and he showed me how to get around this. You see what's going on here, right? We want to prove that V is open because we want to prove that it's a union of open sets, right? And the open sets that I wanted to use were the open sets coming from H. But Reed Barton said, don't use those open sets. You see, this is the axiom we want to use, right? We want a nice fancy collection of open sets. So C is a set of sets, and they're all open. And then this axiom says that their union is open. And what Reed Barton pointed out was instead of trying to use this hypothesis H, I should define C in the following way. I thought this was a brilliant trick. So let's let C be a set of subsets of X there, and it's simply going to be the subsets of X such that U is open U, and U is a subset of V. Right? Oops. V. So this is not the set that I would have used if I was proving this on the board, right? On the board, I would have used the axiom of choice by accident. I would have said, well, obviously, every element in V is contained in some small open set. So let's just choose an open set for each element. We can do that by the axiom of choice. Let's put together all those things there to make a set, and now let's say that the union of those sets is open. So this is a slightly different set, right? Because we don't guarantee that any of these sets I mean, for example, the empty set is an element of C, right? So this is the Reed Barton trick. There. Note that C doesn't just contain the elements, the neighborhoods of X, right? For each X in V. There, C C contains the empty set. Contains more sets, e.g. the empty set, right? So we've got more sets, but it's going to work anyway, because step back a second, stop worrying about what 8 says. Let's just look at this. We're trying to prove that V is open. Let's assume that what we're trying to prove is correct. Let's assume that V is open. Now let's look at all the subsets of X which are open and live in V. What's their union? Their union is clearly going to be V, because V is an element of this thing here, right? I claim that that V is going to be the union, of the C of the elements of C. Now, oops, not that C there. So this is this very clever trick which enables you to prove this thing constructively, right? So so I guess what we are claiming is, we claim, in particular we're claiming oh, do you know what I should do? I should prove that, let's have HC, let's prove that every element of C is open, right? For all U in C is open U, because we're going to need that, right? So this should be obvious. So let's move that down there. So clearly every element, every open set in C is open. Clearly every set in C, because if you look at the definition of C, it says it's open and some other things as well. So I wonder if it would tidy do that? So it was a risk. There you go. I think it's done it. Yeah. There you go. So thanks Scott. Thanks Scott for tidy. And now of course the proof's going to be super slow, but maybe, oh no, it's not so bad. So the reason this is true is because if U is in C, then U is open and U is a subset of V, so obviously U is open. How did it do it? Let's see if I could have done it more easily. Let's see tidy's proofs. It just used simp a lot. Anyway. So now what can we do? So now we can do. So now I claim that so now we're in a position to use this axiom, right? Is open S union, because we've got some C, which is a set of subsets of X, and we've got a proof that for all U in C it's open. So we can now deduce that the union is open, and I'm claiming that that's what the goal says, right? If we look at the goal says that V is open, but the axiom is telling us that the union of the elements of C is open, and I claim that the union of the elements of C is equal to V, and so we can use convert. I'm going to give lean, so what was it called? Is open set theoretic union, right? Is open set theoretic union, and then what do I need to give it? I need to give it a C, and then I need to give it HC, I think. I think this is it. I think that's all we need to do. Oh, blast. Oh no, what? Is open U is in C. For some reason I haven't proved quite the right thing. I'll tell you what, let's not prove that. Let's just do this. Let's see what I must have proved slightly the wrong thing. So now we should have 2 goals. Yeah, now we've got 2 goals. There. So, and let's sort this out. Let's do swap. Let's prove the goal that I was just the goal that I just thought I'd proved. There. So that goes there now. Let's see what's happening here. I thought I just proved. I thought that was exactly HC. Are you telling me that tidy doesn't do this? Yeah, tidy does do it. Okay, so whatever everything's good. So now we claim that V is the union of the elements of C. So now it suffices to prove that V is the union of the elements of C. Clearly every element in C is open, so their union is open. There. So now we've got to prove that V is the union of the elements of C. And how are we going to do that? I think we might have to prove inclusions in both directions. Yeah, we're gonna prove inclusions in both directions, I think. Let's go. Yeah, because we need to use h at some point, and h will only give us one direction. So let's do x of x, right? Let's use set theory. What was the goal here? The goal here is the equality of two sets, right? V is a subset of x, and this union of these sets is a subset of x. So let's use set theoretic extensionality, and now you see I've got to prove that for an arbitrary element of x, x is in V if and only if x is in the union. And now let's split. Oops. Let's see if I can do that. Great. There. So let's prove inclusions in both directions. Let's prove inclusions in both directions. So now what? So firstly, if x is in V, how am I going to prove that it's in the union? This is the hard direction, isn't it? Let's leave this. Let's do the easy way. Let's say x is in the union of these things. So intro hx. So now we know that x is in some. Now this is a union over set. So let's rewrite mem s union. Can you tell that I finally understood all the different kinds of union in lean? Oh, at hx, of course. At hx. There we go. So we've seen all three different kinds of infinite unions in this stream. We've seen unions of sets. We've seen bounded unions. There, we've got mem b union. We've got mem union. I should really write some blog post about these things because I was probably, yeah, yes, James, the cat is complaining. Joel, can you feed the cat? Is that all right? Because she's nagging me, and I'm yeah, okay. Joel says hi, Twitch. So x is, what have I got to prove here? Oh, I see. So now you see hx just says that. Right. So yeah, let's take hx apart. So our case is hx with the cat has gone u hu. Let's see how that's going. So this is huc and then hxu. Right. And so now you see h is in u, and we've got to prove that h is in v, but u is in c. I see. So u is in c, so we can do cases on huc, right? Cases huc with h1, h2. And it'll be one of these. There we go. You see h2 is the proof that u is a subset of v. So h2 is a function, remember? hu is a function that takes as input a proof that x is in u and spits out a proof that x is in v. And what we want is a proof that x is in v, so we can apply that function there. And now we've got to prove that x is in u, but we've got to prove that x is in u. So that's exact. Oh, you know what we could even do? We could probably even put it in here, couldn't we? hxu. Does that work? Oh, h2. That's worked. Look at that. There we go. I thought we'd finished. We've got to do the hard. I've forgotten the hard way. So intro hx. So now we know that x is in v, and we've got to prove that x is in the union of all these things here. So this is exactly, we've never used this hypothesis h before, you see. But you see, this is great, right? Our hypothesis h says that for all x, if x is in v, then something cool happens. And we have exactly an element of x and a proof that it's in v. So let's specialize, and we could just do our cases. Our case is h, x, hx, I suspect. Does that work? It does. With, so now we're going to get an open set u and some proofs about u. So now we've got u as a set, and hu is three things. So this is hu1, hu2, hu3. There. And at least some of these things will be useful. So we're trying to prove that x is in this union, and let's do the rewrite again. How do I prove that that's a set theoretic union? Rewrite mem s union there. What have I got to prove? I've got to prove that there exists some subset of x such that so that's going to be u, right, isn't it? It's bound to be u. It's bound to be u. Let's use u. I should think before I write. So now we've got to prove that u is in C and that x is in u. X is in u is easy. And now what does it mean to prove that u is in C? But C is defined to be, u is in C means is open u and u is a subset of V. Oh, so this is great, right? So this is exact. Well, let's just use u is in C means is open u. So it is so we can use HU2 there. And now we've got to prove, and now this is exact HU3. And what's left? And this is exact HU1. There we go. HU1, comma, has worked. So now that proof is compiled, which is great. So there we go. 14 minutes left, and I've got to prove a big theorem. One of the main theorems of, topology lecture course. So we've proved that a set is open if and only if it's locally open. Did we use any tactics here? Oh, I was going to say we could turn this into a. We're very close to being able to literally turn this into a function. I kind of like turning proofs into functions. Yeah, but somehow we don't quite. What's the proof? What did we use? Mem S union. Is that true by def? What's the proof of mem S union? Oh, it's ruffle. Oh, ha 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 ha. Right. I'm not gonna embark on. I'm going to spend the last 14 minutes turning this proof here that a set is open if and only if it's locally open. I'm going to turn that from a tactic proof into a function because it's good for the soul, right? I think this is a function, and we'll prove this next Tuesday, and then we'll do something else. Let's prove that this is a function. Great. So what we're going to do first is so this proof goes like this. It's this, right? So this is an exit there. So we've got to prove an if and only if. So we've split this function up now. We've got two goals, right? And our first goal, yeah, we've got two errors. So this is kind of weird, right? We've now got two errors, and our first goal is this way, and our second goal is this way. And so now this way, let's do lambda HV, comma lambda HV and x and HX, comma blank. You see, I'm just following this proof, right? I've carefully documented the proof, so it should be easy to figure out what's going on. And so now we're going to work on this first goal, and this first goal is there exists a U. There exists a U such that something or other. And so now we're going to use HV. So the proof will be it's use V, comma something. How does that work? There we go. And now we've got to prove these things here. X is in V, so you can see that's HX, comma blank. And now we've got to prove that V is open, so that's HV, comma blank. And now I've got to prove that V is a subset of V. So we did that. That was closed by REFL, which is a tactic. So now we need to come up with a term mode proof that V was a. You see, we could put by REFL, but that's cheating, right? Because that's not a function, that's a tactic, right? So how are we going to prove this? How are we going to prove? It's going to have a name, right? It's going to be called subset.refl or something. There we go. Subset.refl V. How about that? There we go. We could even put an underscore. So that's done the easy way. And now this way, we do lambda h, comma blank. So now we're going to let C be that. I'm not going to define that C. Let's just, that's going to be, okay, that's fine. C is going, oh no! Oh no, I use convert. Oh no! Okay. So we're going to have to do the assume, right? Oh, how annoying. Oh, it's not going to be a function. Let's assume. Meh. Oh, and I use tidy as well. Okay, so what I'm going to do here, let's see if I can cut and paste it. I'm going to put begin there, then I'm going to put end there, and now here I've got to put this proof here, and I suspect that I can just cut it in. Let's try cutting it in. And I've got some problem with, I should probably delete that. Oh, there you go, and it's compiled. So there you go, I've half turned it into a function. Oh, maybe I should leave that. I've half turned it into a function, but my convert, convert is kind of a high-powered tactic, and tidy is a high-powered tactic as well. But the tidy we can get rid of, right? The tidy we can do that, you see. The tidy's gone completely. Yeah. Oh, everything else I could have done. Can I pull off this convert? 2 goals. Can I do this? Is that not a thing? I don't know how to do it. Okay, I'm not going to do it. Let's start on the. Let's comment this out. Let's comment that out there, and now hopefully we've got no errors. Right, now let's start on this proof. So I claim that a compact subspace of a Hausdorff space is closed, and great, let's go. So what's the goal? Is closed C. So let's unfold is closed. What does that? What does that even say? It says that the complement of C is open, and so what's the math? Let's start with the maths proof. How are we going to prove this? We're going to prove. Oops. We're going to prove that this complement of this compact set is open by showing it's locally open, right? There. So let's. So how's this going to work? So let's say X is in the complement of C, right? i.e. X is in X. X is in X, and X is not in C, right? We want an open set, so it suffices, if we can find an open set, an open subset U, subset of C, of this thing here, with X is in U, then we're done, right? So how do we find such a U? By the previous lemma. So maybe I should just do that now. We could rewrite open if locally open. We may as well just do that now. There. So now intros X and then HX. So there we go. So now you see we've got an X of type X, and we've got a proof that X is in the complement of C, just says X is not in C, right? So if we can find an open subset with X in U, then we're done. So that's exactly what we have to do. We have to find a set such that X is in U, and that it's open, and that U is a subset of CC. Okay, so where do we find such U? Now is where we use compactness, right? So how are we going to do this? We're going to cover C by a bunch of open sets. And where do we get them from? Where do we get the open sets? We get them from Hausdorffness then. Right? So let's say Y is in C, then X is not equal to Y, right? Because X is not in C. There. So by Hausdorffness, Hausdorff, X is going to be contained in some set, V1, and Y is going to be contained in some set V2. There. And they're disjoint, and X is definitely not in V2, right? Not in V2. Do you know what that's a? Isn't that slightly weaker? Is this statement too strong? Is there some, I'm just wondering whether is there some, what's T1? I'm just wondering whether I'm proving the wrong theorem here. Anyway, this is what Ray Licorice told me the theorem was. X is in V1 and Y is in V2, and in particular, and these are disjoint, and V1 intersect V2 is the empty set. There. So in particular, X is not in V2, right? So the union, so of course remember this is V2, you know, equals V, this V2 depends on my choice of Y, right? The union of the V2 of Y covers C. Covers C because Y in C was arbitrary. Yeah, arbitrary, and Y is in V2. Y is in V2 of Y. There. So there's a finite subcover. And so you see this could be, yeah, now take the intersection of the corresponding of the corresponding V1 of Y, right? There. Finite intersection of open sets. It's open and misses and completely misses V. So it completely misses C. There. So that's the proof, but with 3 minutes to go, I'm not going to make it. So what are we going to do? Where can we start? I mean, maybe it's just not worth embarking on this. So I realized when we were going to start that the first thing I needed was this locally open lemma. So I think I'm just going to stop here. If there's any questions or comments, I'm happy to take them. But then, of course, as usual, I'm off to the Discord because it's Xena time. So I'll send a Discord link. There's that. Oh, I changed the Discord link. Let's see if it still works. There we go. Exciting new Discord link to the same server. Oh, I'm lost. Oh, what have I done? Oh, here I am. I'm found again. See if that works. I should still link to Xena Discord. Maybe I'll goof around with this a bit at Xena, and then give a polished proof next time. Right.